continue. So from early 17th century, India's diamond production declined and Brazil dominated the market. And thereafter, from 1800, there was a boom of diamond in the market when South African mines were discovered. And in the last 50 years, scientists have learned a lot of information about diamonds from the transportation history, which has made the prediction of locations for new diamonds very easy. Hello, Mr. Mr. Ashok, please, could you please tell everyone to mute their mics? Mics need to be muted, please, from your side. Thank you. So, and on the right side, I have given you pictures of some very famous Indian diamonds. As you can, we all know the name of Kohinoor, but the Hope Blue or the Dresden Green, Stancy, Regent, Daryanur, Shah, these are all actually Indian diamonds, and they've all made their way to European markets or to American markets, and they were eventually in them. So the Hope Blue is now in Smithsonian, and the Dresden Green is in Germany, and we all know the story of Kohinoor. So we possess none of these anymore, but they have all made their ways. Now I will come to the natural diamonds and how they are formed. So diamonds actually are very, very special minerals. As I
Class like
excuse me, could you please mute your mic, Mr. Ashok?
आगे बीएससी में लगा एमएससी मस्सी हदी होता है
They're not. So should I continue? Hello, should I continue? Yes. So diamonds are very special minerals, as I told you, because diamond formation is very tricky. Diamond requires a lot of pressure for its formation, but it requires relatively low temperature. Diamonds are formed at depths of more than 140 kilometers. Okay, so which could be the probable areas for diamond formation? We are talking of enormous pressure, but relatively low temperature. So these could only be under the cratons, right? Because the cratons are the relatively stabilized parts of the earth, and they have a huge thickness of sediments over there, but then they are not under active tectonics, so you have very low geothermal gradients in the cratons. So actually these are the places where diamonds are formed. You are dealing with high pressure conditions but relatively low temperatures. In addition to diamond formation, there are two things that are very essential. One is you need to have, diamonds are basically carbon, so you have to have carbon rich fluids there. Okay, and where do you get this carbon rich fluids from? Of course, from the mantle convection. So the crustal rocks, the carbonates, they all get down to subduction processes, and under reducing condition, you have to have the carbon part separated. So then only you can have crystallization of diamonds there. So the melt of the fluid must become reduced enough so that there's no oxygen in the system to combine with the carbon. If it is combining, then you will either get carbonates or it will go out as carbon dioxide. So this is and how it is in place now. So below the lithospheric mantle, there are thick plates, these are called the mantle keels, and they extend up to depths of 250 kilometers. And in these areas, it is said that these are the places where diamonds are formed. So diamonds, actually, it is believed, many scientists believe, and in published literature, they say that in this lithospheric, this mantle keels, there are actually the storehouse of diamonds. There are lots of diamonds formed and crystallized and sitting there, just to take a ride in a kimberlite or lamproite, and then it will be carried to the surface. So diamond formation is such. But then diamonds crystallize, and of course diamonds, as I told you, it is the magmas that originate from deeper within the mantle. When they pass through these lithospheric routes, they bring up many xenocrysts, okay, minerals. And along with this, they carry the diamonds from the mantle keels. So there is a misconception that kimberlites are actually the rocks in which diamonds are formed. It is not so. Diamonds are formed in peridotites or eclogites in the mantle, and they are sitting there in the mantle keel, And then during transportation or formation of this kimberlites or lamproids, when they ride up, they actually take the diamonds for a ride and they bring it to the surface. So this is how diamonds take the ride and come to the surface. Diamonds, as a result, often bear signatures of minerals within which they are formed. So the rocks in which there's original rocks, they have inclusions within diamonds. So studying an inclusion in diamond, you can say whether it was in a peridotic rock or whether it was in an eclogatic rock. So you can precisely say that. I'll come to the details later. And as I told you, mantle convection plays a very strong role for the circulation and formation of diamond. As you understand, the availability of fluids, which forms the diamond, and the return of the diamonds from the mantle to the surface. So this is how diamond is formed. Right? So these are the host rocks of diamond. Diamonds can be formed in peridotites and eclogites. These are lithospheric diamonds or the cratonic lithospheric mantle. Diamonds have also been found to be formed in the transition zone and the lower mantle. And these are some precursor minerals which help us, this red, purple, red garnet, when we get this chrome pyrope or this clinopyroxene, this chrome dioxide. These are actually the indicator minerals. When we are looking for kimberlites, we look for these minerals. And in the eclogite, of course, it is a higher, you are having this typical clinopyroxene, that is the omphacite, and pyrogarnet. These are the EX minerals for eclogite. And along with that, you have some amount of grossular and almandine. So this, and you also get within diamond signatures, whether it is eclogitic or peridotic. I'll come to the details later. So now coming to the structure and the properties, of course, it is forming under huge temperature conditions relatively. So you will have a very perfectly balanced cubic system of crystallization for the diamonds, okay? Or any other alteration of the basic crystallographic cubic shape. Yes, yes, that is the cubic. And then it is obviously, this cubic system will be the hardest, and it is virtually inert and resistant to alteration, and it occurs as single crystals or aggregates or clusters. We are only fascinated by the single crystals, but nevertheless, diamonds can form as aggregates or as clusters. The hardness is nevertheless hundreds, so these are used in abrasive industries or in batting. So, but we mostly prefer the single crystals. So coming to the properties of diamonds, yes, it can occur in any colors. We are only looking for the white color, that's the commonest. Then, but you can have yellow, brown, pink, red, green, name any color and you have it for diamonds. But if yes, 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 sir, I will come to that in details. So, and then you have this adamantine lustre, and because it is a cubic system, you are supposed to get it as an isotropic. Across polar, you are supposed to get it isotropic. But interestingly, because of total internal reflection in diamond, you will never get it as an isotropic. That is, it is not becoming black under cross polars. Okay, so you will see an anomalous double refraction. The picture that I give you here, so it indicates that. Okay, this kind of a feature, you'll get a multiple colored phenomenon when you do across polars under the microscope, if you see. Now coming to morphology, as I told you, diamonds can exist as single crystals, as aggregates, or as clusters. And this monocrystalline or fibrous or polycrystalline, these, the crystal structure itself is sensu stricto of certain areas. So starting, if we get monocrystalline of octahedral shape, then we can say that they are typical from Russian mines or Canadian mines or from China or Sierra Leone of Africa. The Indian diamonds are mostly of dodecahedral shape. So just from the basic morphology, from the shape also, sometimes we can say from which area or which where it was formed. So morphology plays a very important role. Okay. So these are some morphologies. Some monocrystalline diamonds can be of basically three shapes. The cubic system of crystallization. So you have octahedral shapes. You can have these eight-sided crystals. You can have cubes, and you can have rounded dodecahedrons. Dodecahedrons, again, the octahedral shape, it indicates this layer by layer slow system of crystallization. So the shape itself, if you see an octahedral diamond, now you know how it is formed, right? When it is a cube, you know it is formed out of supersaturation. Carbon was supersaturated. It was a supersaturated carbon melt from which cubes will be formed. And dodecahedral shape is not a natural shape. It is always a resorption phenomenon. During exhumation or during after it is formed, it will be corroded by the residing fluids, surrounding fluids, and it can form due to transportation process. So it's talk a lot about the conditions of formation. These are some of the samples in which I have worked. These are from the Panna mines, and you can see so many shapes are there. You have perfect octahedrals and dodecahedrals, and you have some cubes, and you have some angular irregular crystals and different colors also. So these are some of the samples. These are the typical monoclinic shapes, that monocrystalline shapes that you can have. The first picture shows the octahedral, the dodecahedral diamond. Then you have the octahedral one. The green wall is again an octahedral. There is a distorted dodecahedral, distorted one, and in the second row, first two, you see these are all twin crystals. They are stars, and then the triangle is actually called a Mackle twin. So it is a distorted star actually. If you orient both along the c-axis, then you get this feature. So it is a graphic Mackle twin, and last two are the distorted forms. So you can have so many shapes, and now you know which form is formed under what condition. Now, the fibrous and the polycrystalline diamonds, as I told you, they have hardness of 10, but nevertheless, a lot of research is done on them. They are used for research purposes, but not as in gems or jewelry. So they are used as abrasives, or the Borch diamonds that we use in the as diamond cutters and in abrasives. So they are mostly used for these purposes. Now, the color of diamond also plays a very significant role. So you can have any colors, as I told you, and all colors signify something. Like it can be due to the presence of certain molecular impurities or atomic impurities. It could be due to lattice imperfections, color centers, natural radiation, or plastic deformation. A white natural diamond is mostly without any impurities. When it is of yellow color or pale yellow color, it has nitrogen for sure in its lattice. If it is a blue diamond, it will have boron in it. If it is a pink diamond, we have a very beautiful pink diamond assemblage which has been discovered from the Argyle mine of Australia. That is the only mine producing pink diamond in the world. So we have beautiful pink diamonds and brown diamonds. These are actually indicating lattice distortion. Okay, the green diamonds are because of irradiation. So you have some radioactive mineral within the diamond's lattice, maybe uranium or anything like that, and it is causing irradiation, giving this, imparting this green color. And black color is absolutely due to complete plastic distortion of the crystal lattice. So all colors have a lot of story to say. Fluorescence of diamonds, these are some studies that we carry out as geologists under short and long UV light. So we are using either 265 nanometers wavelength, or we are using a 365 nanometer wavelength of light to study the diamonds. And diamonds, actually ultraviolet light, when it is used, it interfaces with the elemental impurities and imperfections of the lattice and imparts these kinds of radiating colors, this kind of fluorescent colors. And you can see it is amazing, and you get them in a wide range. So this is a very interesting thing. And also the color of, like I told you, I forgot to say, and the fluorescence of diamonds also help us to differentiate natural diamonds from synthetics, because synthetics will have some specific colors or zonation factors in fluorescence, while natural diamonds will not. So I will come, when I will discuss compare natural diamonds with synthetics, I will come to this topic again. These are some surface features of diamonds. These are from my project work. Actually, these are from all photographs taken by me during my project. So, however smooth diamond surface looks, if you zoom it under a microscope, you will see the surfaces of diamond will have lots of superficial features. The first features are showing trigons. So these are some dissolution features or yes, 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 sir. Yes, sir. These are all triangular shapes. Yes, 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 sure. So hydrofluoric acid, very high concentration acid. Yes, yes, hydrofluoric acid is required. And then you have this kind of pyramidal hillocks, this H pits, this hexagons and trigons and flow lines. So also many surface features, and they all speak of different environments. So these are also some features that I've taken from my photograph. In the first picture, you can see these are formation of tetragons.
These features are matching with the same surface features to get surface of the coast.
Yes, yes, sir. I've seen that. Similar, sir. Yes. Yes, sir. Yes, sir. I've seen that.
I have published the paper. More or less, these features are very much
Very similar. Yes.
on the continental surface.
Yes.
Very
Very interesting. So, we got this kinds of tetragons, and in the previous picture I showed you the presence of hexagons. So you can have trigons, hexagons, tetragons. You can have each pits. You can have this kind of like drain type of structures, drainage type of things. These are ruts, drainage like each pits. And you have this kind of tatami graining. This is under cross polars. When we see this kind of like a microclean has this kind of cross hash twinning. So diamonds also sometimes they show these kinds of features. So and each feature has a lot of story to say. Like the surface feature of diamonds tell us the conditions in which it was formed and what processes it suffered during its transportation. The trigons, tetragons, and hexagons all indicate etching of the crystal surfaces by corrosive fluids at temperatures of more than 1,000 degrees. The microdiscs that are formed, sometimes there are bubble wraps on diamonds, they indicate late stage etching. And places where you have these bubbles, those places are actually unaltered. Then you can have deformation lines. I showed you in the pink and the brown diamonds. If you zoom them under the microscope, you will find presence of deformation lines, which indicates again high temperature conditions and plastic deformation. And you can have this kind of etch pits or solution pits and corrosive fluids that all takes place around 1,000 degrees Celsius. So from the morphology, we can say a lot of things. Like from the shape itself, we concluded so many things from colors, from the fluorescence, and also from the surface morphology. Now, this is another set of information that a mineral diamond shows us. That is the presence of inclusions. Okay, so these are inclusions. You have two types. You could have mineral inclusions or you have fluid inclusions. I will be covering only the mineral inclusion parts here. So, yes, sir. And I do not know much, sir. So I will only talk about what I have done. So what I know, yes. No, sir. I know very little of fluid inclusions. So, but there are two types of inclusions basically. So you can have mineral inclusions or fluids. And in this aspect, I'll be discussing of the mineral inclusions that I found in diamonds and what fascinating work has been done on mineral inclusions in diamonds. So mineral inclusions in diamonds have received a lot of attention over the last few decades because they are the pristine samples from the Earth's mantle that are otherwise inaccessible, as I told you. There is a lot of information about the geology of the Earth's interior. The mineral inclusions act as powerful tools to decipher the origin of diamonds, and it has immense value in diamond mining exploration, so locating new diamond locations in the world. So these
mineral inclusions also have potential to identify which one is the false diamond.
yes, sir, of course. Yes, the natural and synthetics we will differentiate based on. Yes.
Hello friends, chai piyo.
Yes. But nevertheless, for jewelers, for gemology industry, these inclusions or blemishes are considered as curses. But for geologists, we would really like to have diamonds with inclusions. These are some of the inclusions as I told you. These are some peridotic mineral. I told you diamonds can form in peridotites or eclogites. So if it is a peridotic diamond, you will have presence of colorless olivine. Okay, there are some specific set of sensu stricto mineral assemblages for a peridotite or an eclogite. So presence of these kinds of inclusions, like the first diamond, you have some colorless olivine. You can have presence of garnets. You can have a chrome pyro, like the last picture, the pink purple color. You can have inclusions of linopyroxene. So these kinds of assemblages, you can say a lot about what is the source rock for the diamond. Likewise, if it is an eclogitic diamond, then you can have presences of sulfides, which will be having actually sulfide are present. Sulfide minerals can be present in both. Yes. So that is why, yes. But for us, for research purposes, yes, it is very good. It is very good. Yes, sir. Yes, sir. But that is what, sir. Yes, it decreases, sir, because the jewelers they don't want the blemishes. And what they do is they actually do, sir, what they do is in several samples we have seen they put in laser and they burn down the inclusion. And yes, that is how they, because if you cut it, then you spoil a lot of the sample. So they usually do laser drilling and dissolve the impurities. That is how they are managing. But this is another interesting set of inclusions that we get in eclogatic diamonds, that is the presence of sulfides. Sulfides can occur in both perioditic and eclogatic diamonds, but then you have a proportionately relative proportion of nickel probably is different. I have to just check in the literature and tell you, confirmed. But you can have these kinds of inclusions, and you have alendine garnet, you can have presence of corundum, which is another very deep-seated mineral, which you can have inclusions within eclogatic diamonds. So, and you can have onsites, as I told you, typical minerals of eclogite. So, and for the sublithospheric diamonds that is formed at 250 kilometers or beyond 70 kilometers depth, you will definitely get presence of ferropericlase, that is FeO. You can have presence of magnesium and calcium perovskites. These minerals, if they are present, then they definitely tell you that they are a lower mantle assemblage. So this is a published literature from where I have given this. So if it is a peridotic suit of diamond, then you will have the presence of olivine, pyrogarnet, orthopyroxenes, CX, bromides, and sulfides. If it's an eclectic suit, you will have pyrope, almandine, clinopyroxene, sulfides, cyanides, and sanidine, poisite. It's not just one mineral that will help you to identify. It is a combination. So it is you. Yes, sir. Yes, high temperature. Yes, sir. High temperature. Yes.
Sometimes your confidence is very much required
Yes,
to
yes,
interpret the data.
yes. And
Once upon a time, I got the XRI result from the university lab.
okay, sir.
They presented that the result is having this coesine.
Okay.
I thought that okay, from here this is wrong. Unless you know the background,
Yes,
unless you
yes.
know the
Yes, yes, sir. Yes, sir. So like maybe you're only getting one kind, and then you cannot just like blindly say I have got an eclectic. It's a complete assemblage that you need to have. Secondly, it has to be tallied with the morphological features. It's a complete package by which you can actually say what assemblage you're getting. So this is an alert actually. And if it is a lower assemblage, then as I told you, you should have ferropericlase or magnesium perovskite, calcium perovskite. These minerals are essential. So this is again from my project. And in that actually I got two phases for the exhumation of the from the inclusion studies. I got essences of this coesite and chalcopyrite and several other mineral phases which were actually assemblage and the texture morphology together with HIR studies and Raman spectroscopy. I concluded I got an eclogite, an eclogatic ashes. Okay, and in another assemblage I got the presence of magnesium perovskite, calcium perovskite, and ferropericlase. That was the lower mantle acid. So I could say that there was a dual mode of formation of diamonds with a complete morphological and mineral inclusion, and of course using the high-end instrumentation. I could confirm that there were two packages of the diamonds, and the diamond standard is 1332. So I have given this a reference because this will have relevance in the future course of my discussion. So now, basically, I have covered the parts of natural diamonds. Yes. Now, because there is chance of mix with the synthetics, so we will discuss a little bit about synthetics. So why synthetics? Synthetics actually, there was a huge demand for diamonds, so synthetics were prepared. And originally, all synthetics were prepared for a global purpose. They wanted not to exploit the natural resources for industrial purposes, so they wanted to make synthetics. But then, because synthetics looked so good, so they came back to the markets and mixed up with natural diamonds, and that's how many things were cheated and people were cheated. And internationally, of course, there are forums like CIPJO and others where it is clearly mentioned legally that synthetics have to be disclosed to the public, but unfortunately such bodies don't exist in India, and Indian buyers are often cheated. So this aspect from here, I'll be covering some disclosure things that though not disclosed, but we can understand what is the difference between natural and synthetic diamonds. Synthetics were prepared first in 1953 by a Swedish firm, electrical farm, and they prepared it from graphite. Then another time in 1955 it was prepared. Presently 80 tons of synthetic diamonds are being prepared by GBers. So
Yes.
yes, a huge demand is there, and basically globally they are using two synthetic for synthesis of diamonds. They are using two methods. One is from chemical vapor deposition, that is the CVD, which is very common in the market. There are a lot of these mix-ups in natural diamonds. They are just perfect. Compositionally, they are same. They are not able to replicate the crystal structure. What they do here is they are actually reducing methane, CH4, with hydrogen under a very high temperature pressure vacuum condition, and they keep seed crystals of diamond here, and basically the carbon, it forms a melt and it drops on the seed crystals, and they come out as flakes or as slabs like this, and they are recut and polished in 56 facets like a normal diamond, and they are sold in the market. So CVDs are really very difficult to identify. The other category in which they are doing is from high pressure. So CVD is very difficult in laser Raman. Yes, sir. But HPHT can be identified. Yes. Because in HPHT, the high pressure, high temperature, they are using actually graphite, which is an allotrope of carbon, and they're simulating the diamond formation. So they give high temperature pressure condition, they introduce some metal fluxes. So that is how they're creating. So often the HPHT, because they are introducing to very high temperature pressure, so there is a peak shift in Raman. So HPHT can be identified using Raman. Moreover, we often get presence of metal fluxes within synthetic HPHT. So I will show you, sir, some of the pictures. No, sir, you cannot, because refractive index, our refractive index is from up to 1.8. Okay, normally the ones that we use. And diamond as such has a refractive index more than 1.8. So for diamonds, when we use the refractive index, we say greater than 1.8. But then you have another index that is a quantitative, only you have the RI, that is the refractive index, or the specific gravity for any mineral. Others are all qualitative indices. So the quantitative other parameter is specific gravity, and for diamonds it is 3.52. 52. Okay, the specific. And for synthetic diamonds and natural diamonds, the specific gravity is same. It is 3.52. So it is no way you will be differentiated.
That is possible to get limited.
Because because actually you see they are actually simulating the earth conditions. They are and they are using the same melts. So fluorescence में कुछ differences है sir. I will come to that. Sir. See, that is why I covered the first part with the naturals, because I can show you the differences. So this is the high pressure temperature where graphite is actually converted, subjected to high temperature pressure to make it into a diamond. So we often get presences of evidences. This is another interesting mix-up, which is compositionally totally different. This is called a moissanite. Okay, synthetic moissanite. Moissanite is a natural mineral, and it is also a very high temperature pressure mineral that is found in the mantle. So in the Earth's mantle or in meteorites, we get moissanite, and Henry Moissan was actually the scientist who discovered in Canyon Diablo meteorite, from where we have actually standardized. We have that Canyon Diablo is an iron meteorite, which has been used as a standard also. So in this, he found this mineral there, and also in lower mantle assemblages we get moissanite, but it was synthetically produced, and it is a better looking substitute for a diamond. Actually, it has more fire and brilliance than a diamond, but it is compositionally different. It is silicon carbide, so it has a different specific gravity. So in this case, the specific gravity you can differentiate, and of course its hardness is different, and it has very different properties from a diamond, but it is absolutely a look-alike. So now how you differentiate between a natural and a synthetic diamond? Basically it can be used, the differentiation processes are, it is variable. These are some general ways that I have written, that one or two of these will definitely be there. So color zoning would be one factor by which we can differentiate. UV fluorescence could be one interesting factor by which we help to differentiate them. There could be internal graining, presence or absence of intuitions. Magnetic properties are there sometimes, and Raman spectra could be helpful. So this is a fluorescence of natural diamonds. These are from our labs. So these are the natural diamonds. And you see the first row is showing actually some uncut diamonds. And you see fluorescence, you are getting it in shades of green and blue. Now I told you if it is blue or green, like I told you when it came to color, but in case of fluorescence also I can tell you now. So when you see a blue fluorescence under UV, also with nitrogen in lattice, so only colorless and pale yellow diamonds will fluoresce blue. So if you have lattice defect of nitrogen in the lattice, then they will fluoresce blue. If it is green, then it is mostly due to passive formation. So the deeper mantle diamonds or the lower mantle diamonds will fluoresce green. So it indicates definitely high pressure temperature conditions. So these are cut diamonds. They are also showing this kinds of fluorescence. Yes. Then also, sir, it is. I'm not telling you. Always you have to remember one thing: not just by fluorescence you will characterize. Then you can be tricked. I will show you. You have to think of all the factors, and cumulatively you have to account for it. Fluorescence, but like if you get blue, then blindly you can say it is natural. But if it is green or yellow, then it becomes tricky. I'll show you some pictures and you see. Like this is a synthetic diamond, and you see I showed in the previous picture there is a green diamond. This is a natural diamond. But then you see this color is different. So there is a change in the intensity and the hue. And the other interesting thing is often you get this kind of sectorial fluorescence patterns in synthetic diamonds. So this sectorial feature will help you. When you see these kinds of features, you have to know that definitely they are synthetics. And inclusions, I have shown you a lot of pictures of mineral inclusions in diamonds, in natural diamonds, but in synthetics, this is the way you will also get inclusions there. As I told you, when they are doing HPHT diamond, they use catalysts, metal catalysts. You can have in the last picture, you see the blue one. There are actually bottle shaped features. These are actually metal influxes. So some catalysts have remained within the metal and they are found there. Sometimes you can have this kinds of pinhole inclusions or this kind of cloudinesses within the diamond. Then you have to be alert that probably these are not natural. So this is how there are some alarming features. And when it is a natural, you see how clear the crystallographic systems are. You see it is a graphite, because graphite and diamond are allotropes. So probably the first picture indicates that the diamond was formed at such a pressure condition where both graphite and diamond are crystallized simultaneously. Yes, yes. So you are having inclusions of graphite within the diamond, and the red one is again a chrome garnet, chrome bearing, and you can have the last picture is very interesting. It is from one of my slides where I got a perfect dodecahedral diamond inclusion within a diamond. So how it was, and of course in Raman spectra, as I told you. See, the standard peak of every mineral is characteristic of Raman. In Raman, all minerals have a specific peak. So diamond has a specific peak of 1332. Okay. But when we study certain synthetic diamonds, that is HPHT, you see there is a higher value, there is 1345. So when with this, we can identify or differentiate a high temperature, because with the increasing pressure and temperature, there is a lattice distortion, and then the peak of standard peak shifts to higher ends. So this is there has been a lot of published papers on this by Bopart et al. It shows this. And this is the other lookalike that I told you, diamond and moissanite. This is very interesting. Under a digroscope, they are putting this, and in under light you see the white star that you are seeing there is a diamond. So diamond will always glow in a white light, while moissanite will show you this rainbow effect. And other than that, also the specific gravity, the refractive index is same for both. And of course, moissanite will be anisotropic and diamond will show isotropism with anomalous double refraction. So moissanite and diamond is relatively easier to differentiate, but natural and synthetic diamonds are very tricky. So, and of course, Raman spectra of moissanite and natural diamonds will be different because they're altogether different mineral systems. So diamond will have 1332 and moissanite will have 797 or shifts slightly around them. So it is easier. So these are the ways by which we can differentiate. So this is all. I come to the end of my talk, and this is how mix-ups are, and this is how things are. So yes, you have to understand the natural